method for measuring the bulk hardness of metallic and polymer materials.
There are two types of Rockwell tests. The first one is Rockwell and the second one is superficial Rockwell. For the Rockwell, the minor load is 10 kgf, while for the major load is 60, 100 and 150 kgf. For the superficial Rockwell, the minor load is 3 kgf and the major load are 15, 30 or 45 kgf.
In both tests, the indenter may be either in a diamond cone or tungsten carbide ball, depending upon the characteristic of the material being tested. The most common indenter type is a diamond cone ground at 120 degrees for testing the hardened steel and carbide. Next, for the softer materials are typically tested using a tungsten carbide ball ranged in diameter from 1/16 inch to 1/2 inch.
Next is the purpose of Rockwell testing. First is used for material evaluation. Second, available for some structural alloys such as steel and aluminium. Next is to perform an accurate hardness test on a variety of size parts. And last purpose of Rockwell testing is correlate directly with its strength, wear resistance and other properties.
Why we use the Rockwell hardness test? This is because the Rockwell hardness test is a fast method, making it ideal for quick hardness testing. Other than that, because of its simple process and low cost relative to direct measurement of many properties.
The next is sampling size. Due to the relative high loads used, application of the Rockwell hardness test is generally limited to larger sample geometries.
For the process Rockwell hardness test. Firstly, to start the test, the indenter is set into the sample at a prescribed minor load. A major load is then applied and held for a set time period. The force on the indenter is then decreased back to the minor load. For your information, the minor and major loads can be applied using thread wheels or spring. The indenter position is measured using an analog dye indicator or an electronic device which digital readout.
The Rockwell hardness test, scale C. In this video, we will show how the Rockwell hardness test works using a gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant scale C, a rounded cone made of diamond is used as an indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point. In step 2, the test force is increased by 140 kilopons, which is acting as the major force. This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters times 500. Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine. Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it! The Rockwell hardness of our gear wheel is 55 HRC. This result is displayed on the screen.
Lastly, about the calculation. The Rockwell hardness number is calculated from the depth of permanent deformation of the indenter into the sample. As example, difference in indenter position before and after application of the major rod. What is the history behind the Brinell hardness testing? The Brinell hardness testing was originally developed in late 90s by the Swedish engineer of the same name. He wanted to find a method to control the quality and the hardness of the steel. His solution was to press a railway wheel bearing ball into the material and then measure the size of the mark it left. This method is proof and reliable, and in 90s, the Brinell hardness test was officially born.
What is the meaning of Brinell hardness test? A method of measuring the hardness of material by pressing a chromium steel or tungsten carbide ball, commonly 1 cm or 0.4 inch in diameter, against the smooth material surface under standard test condition, generally between 300 to 3000 kg of force for 5 to 30 seconds.
Common test force range from 500 kg force, often used for non-ferrous material, to 3000 kg force, usually used for steel and cast iron. There are other Brinell scale with load as 1 kg force and 1 mm diameter indenters, but those are infrequently used.
Unit of Brinell. According to ASTM E103, Brinell hardness parameter together with a Rockwell hardness method. This method provides the most repeatable result since the vagaries of optical interpretation are removed through the use of an automatic mechanical depth measurement.
Next is the Brinell test method. The indenter is pressed into the sample by an accurately controlled test force. Then, the force is maintained for a specific dwell time, normally 10 to 15 minutes. After the dwell time is complete, the indenter is removed, leaving a round indent in the sample. Next, the size of the indent is determined optically by measuring two diagonals of the round indent using either a portable microscope or one that is generated with the load application device. Lastly, the Brinell hardness number is the function of the test force divided by the curved surface area of the indent. The indentation is considered to be spherical, with a radius equal to the half the diameter of the ball.
The Brinell hardness test. Using the Brinell method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These two elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The testing machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again and the microscope lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines on the edges of the indentation to measure its diameter. That's it! The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The result is displayed on the bottom left-hand corner of the screen and amounts to 250.
This is the calculation in the Brinell hardness test. The first formula is the Brinell hardness testing. As you can see, the formula is HB equal to 2F over pi capital D minus square root of capital D minus small d. Capital D is the bond diameter, small d is the impression diameter, F is the load, HB is the Brinell result. The formula for the Brinell hardness test is the metal hardness formula. The formula given is BHN equal to 2P over pi capital D minus square root of capital D squared minus small d squared. BHN is referred to the Brinell hardness number in kg per millimeter square. P is the load in kgf. Capital D is steel ball diameter in millimeter, while the small d is the depression diameter in millimeter. The next is the error in Brinell testing. The greatest source of error in Brinell testing is the measurement of the indentation. Due to disparities in apparatus making the measurement, the result will vary even under perfect conditions. Less than perfect condition can cause the variation to increase greatly. Frequently, the test surface is prepared with a grinder to remove surface conditions. The jagged edge makes interpretation of the indentation difficult. There are two types of technological remedies for countering Brinell measurement error. The first system is the automatic optical Brinell scope, such as the Brinell optical scanning system, or also known as BOSS system. It is used computer and image analysis to read the indentation in a consistent manner. The standardization helps eliminate operators' subjectivity, so operators are less prone to automatically view intolerance result when the sample's result may be out of tolerance.
The application of Brinell test. Because of the wide test false range, the Brinell test can be used on almost metallic material. The part size is only limited by the testing instrument's capacity. For the strength, firstly, one scale covers the entire of hardness range, although comparable result can only be obtained if the ball size and test force relationship is same. Second, a wide range of test force and all size to suit every application. Third, non-destructive sample can normally be reused. Lastly, for the weakness, first, the main drawback of the Brinell test is the need to optically measure the indent size. This required that test point be finished well enough to make an accurate measurement. Then, this process is slow. Testing can take 30 seconds, not counting the sample preparation time. That's all from us. Thank you.